In this extension video, I would like to briefly comment on the connection between the Fabry-Perot interferometer and its usage in a laser system. So here you can see a sketch of a laser setup, and we talked already in the lecture about the main components, the active medium, the resonator, and some energy source. So let's have a look at this resonator. It's a Fabry-Perot interferometer. So we have here and here are two planes, and we have constructive interference if this optical length here is, so it's 2nd, with n being the refractive index of the medium in between, d the distance, so 2nd must be an integer of the wavelength lambda for constructive interference of two beams, one going, for example, straight through our resonator and the other one being reflected and then going through. Now let us assume that we have some active medium here which can absorb energy by absorbing photons. Photons are provided through our source of light, and after absorption we have some processes in this medium. The medium could be some solid, but it can also be a gas or a liquid, and in this medium we have processes of de-excitation. So we have an excited state, and when it relaxes back to the ground state, it will emit a photon. And since this is some sort of medium, it has a discrete set of levels of excitation, so we get some discrete energy photons. And now, since we parked our active medium inside this Fabry-Perot resonator, or this interferometer we built, we will only pick those wavelengths which fulfill the condition for a constructive interference within the interferometer. So this is what the resonator is doing. It picks those modes that fulfill the criteria for constructive interference. And if we are lucky, and if we have used several selective media, so we could use, for example, another Fabry-Perot interferometer somewhere in between here, or use some other technique, for example, using a lattice to have something which is also selective with respect to wavelength, in order to end up with something that looks basically like this. So if we project the beam that comes then through this partially transmissive mirror on the right hand side, we would like to have an intensity distribution on our screen that looks more or less like this, right? So this would be a special mode of the laser, the most desired mode, if you wish. It's called the TEM00 mode, which means it's the mode with a radially symmetric intensity profile. So this is the case if your overall setup has this cylindric symmetry. And if you measure the distance, if you measure the intensity as a function of the distance from the center here, you will see that this is basically a Gaussian distribution. So that's the desired mode. And keep in mind that this is the mode that we have if we have a planar wave coming in and we're in this constructive interference situation. So if I change the wavelength a little bit, then this whole spot will disappear if I'm fully deconstructive, and then if I keep on shifting, at some point it will reappear because we again fulfilling the constructive interference. Now the problem is that we also have boundary conditions for our electromagnetic wave inside the resonator in the direction perpendicular to the direction of the light. Now, what does this mean? This means that you might also fulfill the conditions for constructive interference in situations where you're a little bit off. And so there are these transverse modes that come in and which can also be stable. And in projection, this leads to other images of your intensity profile here, which might look like this or even like this. So your intensity is a combination of a Gaussian dependence with respect to r, this distance from the center, but it also has a certain angular dependence, which is described by the Laguerre polynomials in this case. So it's actually the square of the Laguerre polynomials for the intensity. This is the case if your overall symmetry of these resonators is cylindric. The other possibility is that you have something that is, for example, squared in shape, then your angular dependence would be described by Hermite polynomials or squared Hermite polynomials if you're looking at the intensity. So that's what you get in general, but of course what you would like to have is this TEM 00 mode. So this is something you reach by perfect aligning of your mirrors and tuning your setup accordingly. Another slide I wanted to briefly comment on is this slide, slide 24, which shows here on the right side a spectrum. It's actually the absorption cross section in units of centimeters squared as a function of the wavelength plotted in nanometers. And it compares the singulate absorption of some dye we have chosen for our laser to its fluorescence peak. Now, what does this mean? On the left hand side you can see a diagram which shows vibrational levels of some molecule in its, say, electronic ground state, denoted as S0. And then comes the photon and excites. So we are in some excited state, and this excited state of the molecule is an electronically excited state, but it can also have vibrational excitation at the same time. We have learned at the very beginning of this lecture that the vibrational energies are small in comparison to the electronic energies. This is indicated in this diagram by smaller distances between the various vibrational levels in this electronically excited state. Let me link this to a picture for the diatomic. So we take now a molecule which only consists of two atoms, because in this case we only have one vibrational mode, because the only thing that can change is the distance between the two atoms. So this is our diatomic, and let's say that this is the equilibrium distance. Now, under the molecule I am drawing now the energy as a function of the distance between the two particles. So I write here energy as a function of R, and here is R. So somewhere here we have the equilibrium. So if we draw the potential energy surface, it would probably look, for example, like this. Okay. I denote this as S0, so this is the singlet ground state. And in this singlet ground state, we have a couple of vibrational states, which I can draw in this picture simply as lines like this. So we assume, you can see it's in good approximation, a harmonic dependence, and then we know that the quantum harmonic oscillator has this equidistant energy level. So this would be a good approximation, at least for the first few vibrational excitations in this electronic state. And here comes some excited state. We assume it's a singlet state. It's the first excited state, so we denote it as S1. And this state also comes with a bunch of vibrational excitations, which I can also add to my drawing. And now we introduce the photon, which excites our system from, let's say, the vibrational ground state in the electronic ground state to some electronically excited state in some vibrationally excited state. So this is a very typical scenario, because typically the electronically excited states have this tendency to have their equilibrium somewhere at larger distance. Why? Well, you can think of the electron hull or the electron density distribution to be a bit more diffuse in the excited state. And so you see the equilibrium is somewhere at a larger R than the equilibrium in the ground state. Now, another thing we have to explain is why do we have an excitation from the vibrational ground state typically to some vibrationally excited state up here. And this is something we will discuss later in greater detail. it has to do with the nuclear wave function, so the wave function that describes the nuclear motion. If you think back of earlier lectures, the quantum harmonic oscillator in the ground state, its probability, it looks like this, and in some excited state, it would look like this, right? So the general rule here for a successful transition or for a higher intensity in this transition is if the two nuclear wave functions have a good overlap. And since we are shifted in the electronically excited states, because one has its equilibrium here and the excited state, the electronically excited state, has it somewhere here, it is very typical to have this type of situation that you are exciting from the vibrational ground state to some vibrationally excited state. Now these molecules are set up in a way that we have now a certain vibrational relaxation here in the upper level, and we will have a de-excitation which is optically active. So we will have an excitation, a de-excitation back into the ground state. And this is the photon that we are interested in, because this is our fluorescence photon. This is the photon we would like to work with in our laser. So you can see by the length of the arrow that the fluorescence photon has, due to this situation with the potential energy surfaces, this fluorescence photon has less energy, so it's shifted to the red or to a longer wavelength. Therefore, the fluorescence peak is somewhere here, whereas the absorption peak was somewhere here at shorter wavelength. And what makes a molecule now a good dye is the following. First, you would like to have a very good absorption of photons that you provide to your dye. So it has to absorb a lot, and then you would like to have a dye that transforms this into a very broad fluorescence peak. So this peak here should be as broad as possible. Why? Because if this peak is broad enough, then it gives us a lot of variety in the wavelength that we would like to laser on. Okay, so by adjusting our resonator, we can fulfill now the condition for constructive interference for a certain wavelength, here or maybe here. And the broader our fluorescence peak, the more flexibility we have in our system. So you can say that each dye covers a certain range of energy, a certain range of color. So this is now one example. You can see here the laser dye prepared and put in between a resonator which consists of a mirror, can be combined with a etalon, for example, and on the other side a lattice in a setup which is called Littrow. So here you just take the lattice and put it under an angle which fulfills, for example, for the given wavelength, the condition that they say first order, for example, in diffraction is aligned with the optical axis of your setup. Now, what does this setup provide in terms of output spectrum? This is seen here on this slide, where we have a comparison of different dyes, so we can see the so-called tuning curves, giving us a feeling for the effectivity of the dye in a given range. So this is basically the intensity shown as a function of the wave length. So if we look at the picture in the upper right corner, intensity as a function of the wavelength. For example, our dye is of the type, or is the molecule rhodamine B, somewhere in this range here. If we look at the intensity as a function of wavelength, this is our fluorescence band of the dye. And now, by introducing the lattice, but also the etalon, so the Fabry-Perot interferometer, we grab only a specific region. So we are highly wavelength specific, and this is where our laser is then lasering. So this is the frequency range of the laser. We could go even more specific by introducing additional wave selective or wavelength selective tools and put them into our resonator setup. If you're interested in the details of these tools, how they're working and how to use them, I recommend you visiting the lectures of Professor Krenn, Professor Koch, or Dr. Lackner, who are experts in this field of nano-optics and laser physics in general.